signal multiplied by the cosine wave. What this multiplication has? What is the effect of this multiplication into the frequency domain? We don't know this, but what we know, we already know that if we multiply a signal by this complex function, then its frequency domain is exactly the same spectrum but shifted around if not. This is we have already proved now. Now, can we relate this sign into yes? So we know that cosine 2 pi is e j 2 pi e plus e minus j. Is this correct? Is this correct? Divided by 2. 2 is a very important factor here. So it means that this cosine is nothing but this summation. So it means that my signal y of t is the same original signal multiplied by half. Yeah, instead of cosine we substitute for that cosine this term. Nothing but half plus half multiplied by so what we have just done now is just we express the same signal in terms of another two complex extensions. Why we have done that? Because we know this, we know the spectrum of this, and we know the spectrum of this, and we can use the linearity operation of the property of the Fourier transform. So, can we move forward? It is okay. So this means that I know that this. So that x of t ej 2 pi f0 t is right, and I know that what this will be f plus. It means that the spectrum of this signal is 1 over 2 and x shift around positive plus any comments? It is clear that the derivation is clear, right? So this means that, can I move forward? So this means that I have a signal. This is the frequency domain. And this is the spectrum of that signal. It has a bandwidth W. So if this is 1, okay? This is the spectrum of this signal. If the signal in time domain is multiplied by a signal of this frequency if not, it means that the spectrum of the signal is shifted. This is a shift, right, in frequency domain. This will be shifted into the right one, yeah. Around, instead of 0, will be, look at this. Instead of 0 will be around. So everything, the same shape. We reserve the shape. We just shift this triangle from this part, shifted, so this 0 becomes if not, and this W becomes if not plus W, right? And this minus W becomes if not minus W. And exactly the same shape. So we have triangle exactly the same. If this is 1, this must be so this is half. Sorry, it's not to scale, but this must be half of this. So this is the first part. We shift the signal to 0. We shift it into the frequency of the carrier of the sine wave into the positive range, and plus another part, again, the same shape, the same form, the same spectrum, which was around 0, will be shifted around minus. So this is, sorry, must be the same, so this is half. And what's this frequency? What is this point? It's minus, if not minus W, right? What's this point is? We shift this 0 minus 0. Minus W becomes minus W minus if not, so it will be minus. No, it's W. 2W. Okay? So the bandwidth of the new signal is twice the original bandwidth. So when we have a real signal at a low pass multiplied by a sine wave of frequency if not, as a result, the spectrum of the original signal shifted into plus if not and to minus if not, and the bandwidth of the new signal becomes twice of the bandwidth of the original signal. Questions? So to the next property. So suppose that we implement a differentiation. Yes, please. You don't know why? Yeah. You see. So what is the definition of the bandwidth? There are different definitions of the bandwidth. But suppose that in this case, if the signal is limited, I mean, the bandwidth is the range of frequency where the signal is not 0. So you see that it is 0 everywhere except in this positive frequency range. In this case, the signal is, the spectrum is 0 everywhere except at this frequency range. So this is W. Right. So the next operation is differentiation in time domain. It is not difficult to prove that this operation in time domain becomes in the frequency domain a multiplication by the frequency itself. So it means that we enhance enhance the high frequency components, as you will see. The integration is the other way, so the spectrum is just divided by the frequency itself, and proof is not that difficult. This is a function. This is the function of time. This is the inverse Fourier transform. You take the differentiation of this with respect to time. Is it possible to differentiate under integral sign? So if we take the derivative of this function, can we, yeah, so this differentiation, can we take this differentiation inside the integral sign? Because we are differentiated with respect to time, and this integral is with respect to frequency. So taking this operation inside the integral, this is a function of frequency, so this is constant, nothing to do with the time. This is the time, and the differentiation is this. We differentiate with respect to time, so we get J by M, and this is our equation. The same is, okay? The same is for the integration. So it means, this means that if you have a spectrum, if you have a signal, if it is differentiated, what do we do? The higher frequency components will be amplified. So we amplify the high frequency components with respect to the lower frequency components. The same with the integration. Not sure that this is it is required that you know how to prove this property. What is required really is to understand the meaning of that. If you have a signal and you have an operation in time domain, what you need to know is what is the effect of this operation into the frequency domain. Okay. So what I suggest is that next week we have a short quiz for 10 minutes. Okay? So it will be a marked quiz, so we just solve it and then we'll discuss it is an application of today's lecture. So we have a signal. I will give you a signal, the spectrum of a signal in frequency domain, and I ask you to sketch the spectrum of the signal after doing some time domain operations. Okay? So next week will be a 10 minutes quiz. It is option, it is not marked, and it is up to you to solve it or not, but then we will discuss the answer of this quiz. Okay? So this is the integration. And the next important property is convolution. What is convolution? What is the definition of the convolution? Convolution is a very important operation in signals and systems. I'm sure that you have already spent a lot of time with convolution, right? No? What is the definition of the convolution? This is the definition of the convolution. It is this is the notation of the operation, and the meaning of convolution is this integral. It is the first signal. You take a shifted version of this signal, right? It is the same signal, shifted around lambda, and then you integrate with respect to lambda. We integrate with respect to lambda, so as a result, we have a function of time. This is the definition of the convolution. Convolution has a very, very important property, is that the transform of the convolution is product of the transform. Okay? And that's why people in the signals and systems, control systems, linear system analysis, circuit analysis, they prefer to use transform domain. Okay? So people in the signals and systems and circuits analysis, they prefer to use transform domain. Why? Because convolution in time domain is multiplication in the frequency domain, or in the transform domain. The same operation holds for Laplace transform, right? So if you have a convolution in time domain, it is a multiplication in the frequency domain. If it is a multiplication in time domain, it is convolution in the frequency domain. Okay, that's what we need to understand. But what's the definition of the convolution is this integral. So convolution is nothing but this integral. So we have function convolution. So this will be another function t, x of t, convolution. This will be we take the first function, the other function, and minus. So this integration, and what's this t is this t. Okay? This result is a function of time. Please. So it means that if you want to find the function, the convolution at time 0, it is this. Instead of t, substitute 0, so it is. If we see at a given time 1, so it is. So whenever you want a function at any time, you need just to specify time and find it. Yes, please. T minus standard. Yes, sir. T minus. Okay. We'll come back to this when we see the one of examples later on. But this is the meaning of the convolution. It's just the integration. You need to calculate the integration for different values of the parameter t or the frequency data. Yeah, so a convolution in time domain is a multiplication in frequency domain, and this means that this so from this property, please, from this property that products in time domain, if you take a signal, products of a signal in time domain, please. It is a convolution in the frequency domain. And what is the definition of the convolution is this. So how from this definition and this property, we can show that if you have two signals, they are band limited to these bandwidths, B1 and B2. Then if you multiply the two signals together, we get another signal, but the new signal will have a new bandwidth that is twice of that's the addition of the two bandwidths. Let us try to explain this. So suppose that we have two signals. X1 of t that has a bandwidth B1, and X2t has a bandwidth B2. Just for explanation, the spectrum. So this is the frequency domain. the spectrum of the signal is something like this. It is B1. Okay. Signal of bandwidth B1, it is something that is 0 everywhere except this frequency range. Right? So this can be any value, so we're not interested in the exact shape of this spectrum. Okay, so we have a signal x1 of t that has a bandwidth d. Means that it is 0 everywhere except this. And x2 of t is another signal. So this is the spectrum of x1. The other signal, suppose that b2 is larger than b1. Okay? So this is b1, suppose that this is, which is another signal, that is 0 everywhere except in this frequency. Okay? This is what is given. And what we know, that if we have two signals, x1 of t multiplied by x2 of t, suppose that this is a new signal, y of t. And what we need to know is what is the bandwidth of the new signal. That's multiplication of x1 of t and yeah, how to proceed? It is a multiplication in time domain, so in frequency domain it is a convolution. So what we know is this, is that the spectrum of the new signal is convolution. That must be like that, right? Please help me so I might get some. The spectrum of the first signal multiplied by the spectrum of the second, it is D, and the integration is for the ranges where this is not 0, of course. So the limits of the integration is very important here. Okay, so we need the spectrum of the multiplication. So we have these are the two signals, and this is the formula for this. We are not interested into the exact shape of the spectrum. So that's why I will not perform the integration. I will just need to use this property with this to know where or when this multiplication is 0. So suppose that I want to find the spectrum. So let me what is y of 0? This is, you multiply this function multiplied by x2. Right? And this is not 0. You just multiply this function by this function. Right? When you multiply this by this will not be 0. So at 0 is not 0, and so on. Until, if you take f equal to b1, so what is y at frequency b1? This is equal to x1 lambda, x2 b1. What's this? How to find this product? Yes, please. Yeah, that's it. This is the definition of that. This is the operation. Okay. So we have a multiplication in time domain, it is convolution in the frequency domain. If it is convolution in time domain, it is a product. That's it, yeah. So the question is that we need to find what is the function, so I need another graph to plot this. So this is the spectrum Y, right? So we have seen that at 0 it is not 0. Now suppose that we are taking at P1. So what's the value at P1? It is given by this function. And what's this? It is 1 multiplied by a shifted version. So what's this? This is x2 shifted around P1. So if it is, so it is complicated to explain, but it is, so what will we take this? Shifted it to be around P1, right? Instead of 0 will be P1. And it will be the same exactly. So this point will be P2 plus P1. And this point would be P2 minus P1, so it is positive. P2 minus P1, so it is something like. But the important thing is that when you multiply this function by this function, as a result, it's not 0 because there is a part that's not 0. You see this? So you continue with this until you come to a point that is B1 plus B2. So what's the value of the resultant spectrum at B1 plus B2? How to find that? It is this, right? So y at B1 plus B2 is equal to x1 multiplied by x2 B1 plus B2 minus lambda. And what is this? You take this and you shifted this one to B1 plus B2, so as a result we have this. So this is the x1, this is B1. We take the other one, shifted around B1 plus B2. So this will be B1 plus B2. So B2 becomes B2 becomes B1 plus B2, and this would be D. So what is this? This is x2 x minus B1 plus B2. So when you multiply this by this, we get 0, right? So it is 0. This is a value here, not 0 multiplied by 0, which is 0. And this is a value that multiplied by 0 is 0. So we get 0. So this means that this value will be 0 if it is. So we have a value only which is within P1 plus P2. So try to do this yourself. I'm sure that it's not that difficult. Okay? So, yeah. The last part. Which one? Try to draw this in. So we have. This is P1. Suppose that all are P, okay? So this is X1, okay? And this is the other one. Okay? What we need is X1 multiplied by X2 F minus E, or minus 2. So what is X2 minus F2? We take this, shifted it to be around 2, right? So this 0 becomes 3b. Plus b becomes 3b. And minus b becomes 3. So this is the same as. You need to multiply this by this and take the integration. So when you multiply this by this, what you will get? This reconciliation, this is 0. So at every point, it is 0, 0, 0, 0. And this interval, this is not 0, but this is 0. So it is 0 everywhere. So it means that we integrate a function 0 with respect to anything. And the same is when not 2b, but rather than 2b, it is 0. So as a result, the bandwidth of the new multiplication is just the bandwidth of the first signal plus the bandwidth of the second. Okay? So it is the bandwidth. You don't need to know the proof, so it's just for your information. Okay? What you need to know is that if we have two signals, each signal has a bandwidth E1, the other signal has another bandwidth E2, then when we multiply both signals, we get another signal that have the bandwidth of the signal. So it means that if we have the same signal, if it is, we square the signal, it becomes twice of the bandwidth. If the same signal is, we take the nth power of the same signal, so we expand the signal into the The last operation is the scaling. We have already seen something like that when we consider the pulse. See that if we compress the signal, frequency domain it is expanded and it is the other way. So this is the meaning of this. Explain this. This is 1 minus 1, and this is t over. This is x. How we can find this x, 2t and x, t over 2. X2t, what's that? Is it compression or expansion? Expansion, compression. This is x of t. How we can sketch this? X2 of t. What's this? Compression, yeah, right. So this will be compression by factor of 2. So it is 1 becomes half. What is this? T over 2 is that. So 1 becomes 2 and so on. So if it is larger than 1, it is compression. This than 1, it is expansion. And it is the same. This is the meaning of this. So it is A. Whatever A. A is larger than what, please? A could be larger than 1 or smaller than 1. If A is larger than 1, then this operation is a compression, but in the frequency domain, it is the other way. It is because 1 over A will be less than 1, it is an expansion. Okay? So whatever you have here, you have the inverse operation there. If this is expansion, this is compression. If this is compression, it is that. So always we have the inverse operation. Whatever you have in time domain, you have the inverse time operation in the frequency. It's only a summary of what we have done. This is the sinc function, definition of the sinc function. Okay, so be careful about this definition. In some programs they use pi, some other programs they didn't use pi. In MATLAB, I think they didn't use pi. In MATLAB, they have predefined functions, sinc function, but in their definition, it is just sinc x over x. So we are using the programs. Try to make sure what is their definition of the sinc function. But we use sinc with pi. So this is the definition of the sinc function. Convolution in time domain is product in frequency domain. Product in time domain is a convolution in the frequency domain. And this is the bandwidth. Scaling, this compression, it is expansion and the other way. And so, what would be the bandwidth of this two signals? If we have two signals, okay, two band limited signals. What is the bandwidth of this signal? Please. It's 4, and this bandwidth has a bandwidth of 3. So what will be the bandwidth of, when we add the two signals, what will be the bandwidth of the resultant signal is? 1. So we add the two signals. Why 4? Why 4? Yeah, because the spectrum will be the addition of the two spectrums. So 3 minus 3. And the other one is 4 minus 4. And when we add them, so it is an addition in time domain. It is an addition in time domain. What would be the resultant in frequency domain? Addition in time domain is convolution in frequency domain. Yes or no? No. It's not again, it is a multiplication in time domain. It is a convolution in frequency domain. Multiplication in a convolution in time domain is a multiplication in frequency domain. But what if it is an addition in time domain? Addition. It is addition. Linearity. It is the first property. Linearity. So if we add signals in time domain, it therefore transforms. And what if it is minus x1t minus x2t? Again, it is the difference. The difference is the difference. So if this is my first signal, if this is a spectrum y, this is the spectrum of. So the spectrum of the addition of the signal is just the addition. I'm not interested in the exact shape of the spectrum. Otherwise, I must consider at every point. I have to add the spectrum at each frequency, but I'm interested in the bandwidth. So just in the range where this is not 0. We know that this is not 0. So when we add it not 0, this is not 0. It is only if it is, but there is a value here. So the bandwidth is 4. The next is the convolution. So when we convolve two signals in time domain, it is a product. And if we take the product of these two spectrums, what will be the bandwidth of the new signal? 3, right? Because it is a, if you so this is the addition. But if you multiply, you see that this is 0. Multiplied by any value must be 0, so that it would be 3. Okay? And what is the multiplication? It's convolution frequency domain. And if we convolve these two signals, the bandwidth will be. And if we square the first signal, the bandwidth will be. The bandwidth is the positive part, and you have this in the notes, right?
third one is the convolution.
This is the convolution. Yeah. The spectrum is the convolution, but the bandwidth is the summation of the two bandwidths. Okay, is this clear now? This is not a summation of the two spectra. This is the bandwidth. This corresponds to the bandwidth of the new signal. It is not the spectrum of the new signal. Okay? Any questions? Questions? In the remaining 5 minutes, I'll just go very fast through this example. Okay? Second and third. Yeah, this is two signals. Convolution of two signals. Right? And this is the same signal we square it, which is like we multiply x of t by itself. Which is like in the fixed domain, it is a convolution of the spectrum by itself. So now we need to know the spectrum of this signal. You can either apply the Fourier transform directly, or you can just use the properties. So we know that this signal is a rectangular function shifted around minus tau over 2. This is another rectangular function shifted around this minus tau over 2. And we just apply we know this. We have already calculated the spectrum of the rectangular points. And from this knowledge only, you can apply the properties of the Fourier transform to calculate the Fourier transform. So it is linearity, and this is shift. So shift in time domain, shift in time domain, and linearity. So we add this plus this. Take this as a common factor. This is the sine function. So you can use the properties of the Fourier transform to calculate the spectrum of the new signal using something that you already know. But we will start with this next. Any questions? Questions? Thank you.